So, welcome everyone for the next seminar on probability in stochastic process from USP. And today we have Professor Alejandra Rada from Federal University of BC. And Alejandra is a former PhD student here from the USP, in USP. So it's a pleasure to have you again with us, virtually at least. So welcome, Alejandra, and thank you for accepting the invitation.
Thank you for inviting me. And good afternoon, everyone. This is a pleasure for me to give this seminar, and I will talk about the size of a rumor when we have multiple repetitions. This is a joint work with Christian Colletti. He's here now. Ercio Levenstein here too. Pablo Rodriguez. Christian is a professor from the Federal University of ABC. Ercio is from UNICAMP, and Pablo Rodriguez is from Federal University of Pernambuco. I will turn off the camera and turn on in the questions, because my internet connection is not good, and especially in rainy days like today. So sorry. Are you see me? Are you see the presentation, the slides?
Yeah.
That's perfect. Okay, I will start now. A standard model of rumor spreading was introduced by Cayley and Kennel in 1965, and this model is called the Decay Model. And we assume there is they assume that there is a population with n people in total. Those people are categorized into three groups: the ignorant, the spreaders, and the stiflers. And the people interact by various ways contact. So the spreaders are gossipy people that tells the rumor to the other individuals of the population. And when the spreaders has a contact with an ignorant, the ignorant becomes a spreader. If the spreader contacts another spreader, both of them become a stifler. So the result is two stiflers. And if the spreader meets a stifler, the result is the same. We have two stiflers. The spreader, the initial spreader, becomes a stifler. The stifler is who has knows the rumor but doesn't want to continue to spread it, and the spreader are the gossipy people, and ignorant doesn't know anything about the rumor. And this is the interaction that I already told for you: spreader and ignorant. The ignorant becomes a spreader, and the two cases, the interaction between a spreader and a spreader and a spreader and a stifler, the result is two stiflers. That this interaction, the last interaction, are called a stifler experience, and that situation represents the less of interest in propagating the rumor derived for the learning that is already known by the other individual in the meeting. The decay model was generalized for Maki and Thompson in 1973, and their generalization was made modify the way that the propagation is done. So this model is also in a closed population and the same three classes of individuals, ignorant, spreader, and stiflers, but the rumor is propagated through the population by direct contact. What that means? That means that we can recognize in the interaction spreader, the initial spreader, and only the initial spreader becomes a stifler. So the same rules that decay model are kept. Only the difference is the interaction between spreader and spreader. So if I have a spreader and ignorant, the spreader tells the rumor, and the ignorant becomes a spreader. If the spreader meets a stifler, the spreader turns into a stifler. But the difference between this model and the decay model is the spreader-spreader interaction, and in this interaction, the initial spreader becomes a stifler. Generalization of these models have been made considering two options. I mean, the generalization of these models you can make considering changing of the dynamics of the dissemination or changing the population structure, I mean the graph. So generalization based on changing the dynamics of the process were studied for Elcio Levenstein and Pablo and Fabio Machado in 2011, and they assume that each spreader sees the propagate the rumor after being involved in a random number of Stifler experience. And Stifler experience is the interaction spreader-spreader and spreader-stifler. Rada and Pablo and others in 2015 proposed a competition model in which informant try to convey the information while the stifler try to hold it. Generalization based on changing the structure of the population were studied by Christian Coletti and Pablo in 2000 and others in 2012, and they analyzed a rumor when the population is represented by the two-dimensional hypercubic lines. Comets in 2013 and others modellate the transmission of the information on the Erdős-Rényi graph. And Sandro Gallo, Nancy Garcia, and others in 2014 studied the rumors in the natural number set using the renewal process. What is the main aspect? What is an important aspect in the study of these models, of this process? An important thing is to study when the process ends. And the process ends when we don't have any spreaders in the population. What's proved for the decay model and the empty model that when ends goes to infinity, the final proportion of the ignorance is approximately 20%. So what we did in this work, a generalization of the Maki Thompson model, assuming that each ignorant becomes a spreader only after hearing the rumor k times, a certain rumor a certain number of times. Our model involves a multidimensional Markov change, and we establish a limit theorem in the spirit of the how is the proportion of the ignorance when the process ends. We do that analyzing the convergence of a dynamical system suitably defined. So our process is the following. Consider a closed homogeneously mixed population with n individuals. For fixed k, consider the k spread Maki Thompson model in which an ignorant becomes a spreader after hearing the rumor k times. That implies the population is divided into k plus 2 categories, and we have the same that before, ignorance and spreader and stifler, but now we have k minus 1 categories for the I-aware individual. What is I-aware individual? I-aware individual is an individual has heard the rumor exactly I times. So this figure represents the interaction that we have. I have an ignorant. I have an ignorant, and this ignorant meets a spreader. A spreader is with red, and this ignorant becomes an I and one aware. One because he heard one time. Then the process continues until the aware listens the rumor one more time, and he becomes an I plus 1 aware until he hits k minus 1 times hearing the rumor, and the ignorant, the k minus 1 aware becomes a spreader. I have two spreader now. If the spreader meets another spreader, the initial spreader and only the initial spreader becomes a stifler. And if a spreader meets a stifler, I have two stiflers. Okay. So our model is a k plus 1 dimensional continuous Markov chains where xt represent the number of ignorance, yit at the time t, for t bigger than 0, greater than 0, yi is yit represent the number of I-aware individuals at the time t. Yt represent the number of spreaders at the time t, and zt represent the number of stifler at the time t. So we can represent our model like a k plus 1 dimensional continuous time Markov chains, and we can write it like this. We assume that the following limits exist. The proportion, the asymptotic proportion of the ignorance at time 0 when n goes to infinity is x0. The proportion of I-aware people converts to yi0 when n goes to infinity. The number of spreaders converts to the proportion of spreaders converts to I0 at the time 0. And then let us compute the limit of the proportion of the stiflers using this formula, 1 minus the limit that we have here before. This limit, the Taylor limit, we call the initial configuration of the process, and when x0 is equal to 1, we call the standard initial configuration. Like I said before, the remaining proportion of the individuals is an important issue for us, and we want to find her. We find it, and for that we define the absorption time. That is the time where I don't have any spreaders in my population. So if we find the characterization of the variables when the time in the absorption time, we have to analyze this proportion in this time, in the time of the absorption. So I have the number, the proportion of ignorance, the proportion of I-aware people, and the proportion of stifler. Remember, I don't have a spreader anymore, so I don't have Y anymore. Our main theorem is in that way. We prove the proportion of the ignorance when the process ends is x infinite, and when the population goes to infinite, almost surely. This is the proportion when n goes to infinite, when n grows until infinite. The proportion of I-aware people. This x infinite, we will find in the latest slides, but the proportion of I-aware people we can find using this formula. And remember that if by the proportion of the ignorance and the proportion of I-awares, I can find the proportion of stifler using one minus the limits before. Limits here and here. And remember that I don't have any stifler, so I don't need Y. This is our main theorem, and we characterize the proportion, the final proportion of ignorance, I-aware, and stiflers when the process ends. How we prove that? We prove using a technique I will describe now. We define our process, and we denote the process like RT. And the main idea of the proof is define a new process, R tilde, with the same transition as R, and the same endpoint. When we define this new process, we can prove that the entire trajectory of the new process, scaled by n, have as limit a set of differential equations that we can treat. And if we analyze that, the solution of that dynamical system, we can find the proportion that we want to find, the proportion that we are interested. So the first thing that we have is define that new process. For that, we define this time, that is the infimum of the real number between 0 and the time of the absorption, that this is true, such that this is true. And we define the new process like the old process, but in this time. So the new process is a new ignorant, but in this time, the new I aware, one aware, but in this time, until the number of spreader at that time. So we can define, this is a new Markov change with the same transition process, with the same transition that the process, the K spreading Maki Thompson model. And we can define another absorption time for this new process. And we realize that the time of the absorption, the process when the both process ends is the same. So what we have that analyzing this process, we can find the proportion that we want to find. And this book, the theorem, this theorem in this book is the course of the book, the course one. And this reference have this theorem, and that theorem guarantees that this process converts almost surely at some quantity here. This quantity is the solution of this dynamical system. So what we going to do? We're gonna find the solution of this dynamical system with this initial condition. And this initial condition is the condition that we show to you here. We assume that this limit exists. This is the initial condition for the dynamical system. So we find the solution of this dynamical system, and we find the proportion that we want to find. For that, we need, in order to find the solution of the dynamical system, we have to study a transcendental function f. This function is divided in between 0 and 1, and look like this. So I will present some results about this function in order to find the solution of the dynamical system. One of the results is the function when x goes to 0 for the right is minus infinity. So the f assumes negative numbers, values, when x is go to 0 for the right. And f evaluated in x0 is equal to y0 and is greater or equal to 0. Then this f and f is continuous function have to cross the x h, and at least has a 0. So this is the proposition that I have here. F has at least one 0 in this interval, 0 and x0. For that, we define x infinite like the supremum of x in that interval, such as f in x is less than 0. This is the final proportion of the ignorant. So it's important, it's really important to understand how f works. X infinite is a function of k. So when we have k equal to 1, that is the original Maki Thompson model developed in 1973, the proportion of ignorant is approximately 20%. But this number begins to decrease after we increase k. Until 10, the proportion of the ignorance when the process ends is very, very small. Now I'm gonna define this function, because for the f function is important is writing using this function. So consider a G general function in an interval E, I, and C, Gi denotes the number of zeros of G in that interval. So what we gonna do with these two things? We have this theorem for f, defined like this, and here is the lower gamma, the lower incomplete gamma function. For f, written like this, we have 2 zeros if x infinite is less than 1 and x0 is equal to 1. And I can have 1 or 3 zeros depending on x0 is less than 1, and this conditional for the proportion of our initial individuals. So in summarizing, we have 1 or 2 or 3 zeros for this function. I'm gonna show you in this figure like the zeros are depending on f. For k equal to 3, I have in this figure 2 zeros, this, and this is the case when x0 is equal to 1. Then I can have 1 0 or 3 zeros. And this two graphic, this two figure, x0 is 0.95, and we change the proportion of spreaders. Here is 0.02 here and 0.01 here. The rest of quantities are 0. And look at, I have 2 zeros, 1 0, or 3 zeros. And the proportion, the final proportion of the ignorance will be this. In the case of 2 zeros is this, 1 0 is this, and 3 zeros is this. How we prove the number of zeros in the f function? We use this theorem, the theorem from Polya and Sgo. And this theorem said the following: is you have a function writing like a power series, and then of C, the number of changes of sign in the sequence of coefficients of C. Using these changes, the number of the changes of sign minus the number of the zero is a non-negative even number. So what we do, we count the changes of the sign of the coefficient of a S function. How we apply this theorem? We apply like this. We write this. We write f like a function of x0 a minus t, and this is the the power series. So using this function, write it like this, we apply the theorem. So I have the function, I analyze how many zeros it has, I analyze the limits when x goes to 0 for the right, or when x goes to x0 in the another extreme of the interval. I mean here, what I have this and this, and so I know that the function has at least one zero, and now I can count the number of zeros. So with this result, we finally can find the solution of the dynamical system. So we write the proportion of spreaders like f in xt. T is writing like this, and we found the solution of the dynamical system. What we also did is important also study the central limit theorem for the spreading Maki Thompson model. But we also did that for k equal to 2 and k equal to 3. The method for proof is the same for any k, but it's very tedious compute for k bigger than 3. So I will present the central limit theorem for 2 spreading Maki Thompson model and 3 spreading Maki Thompson model. And an important thing is x0 is equal to 1. I mean, we consider only the standard initial condition. And we prove that the proportion, and for the 2 spreading Maki Thompson model, we find the proportion of the ignorance is almost 12%, and the people what is one aware is close to 25%. And in addition, we find the distribution, but we find that the proportion of the ignorance and the proportion of the one aware converge to a two-dimensional normal distribution with matrix covariance, with covariance matrix with this element. And for the 3 spreading Maki Thompson model, well, this is the figure. The normal is like this. It's a pretty normal distribution. For the 3 spreading Maki Thompson model, we find the proportion of ignorance is almost 7%. The one aware people is like 18%, and the 2 aware people, individuals, are almost 25%. And we have 2 convergence in distribution to the 3-dimensional normal distribution with covariance matrix equal to this. And that's it. I have here some reference. If you are interested in this topic, you can write me. I can give you my email, and that's it. I don't know how much time is it. I don't know what time is it.
No, you're good on time. Thank you, Alejandra. Do we have questions or comments?
Yes, I have a question about the well, the result is only for the final time, right? But the auxiliary process that I believe you used, I mean, correct me if I'm wrong. I mean, for that you had a result for all the times, right? A convergence not only for the final time but for the whole trajectory. So my question is about a convergence result for your process, for the original process for all times.
And the convergence is for when the process ends already. The trajectories are the convergence of the entire trajectories. I don't know if I answered well. I prefer to answer in Portuguese. I can? Can I?
Yes, certainly. Sure.
A convergência foi as trajetórias que sofreram a convergência foram as trajetórias do processo escalado. E eles, como eles acabam no mesmo ponto, a gente extrapola para o processo que a gente está estudando, que a gente está interessado. Mas a convergência das trajetórias foi para o processo, totalmente para o processo escalado. Eu não sei se respondi direito, respondi a tua pergunta, Renato.
Ok, obrigado.
A você.
I have a question, but maybe it's a naive question because it's not my background a lot. I worked a little bit only with differential equations. So can you give me any insight about this f function? What this means in terms of your process? Like, if you have any interpretation?
Interpretação, bom, aqui nesse momento eu fujo, não saberia interpretar. Talvez o Christian e o Écio que estão aqui, eles possam melhorar a resposta. O que eu posso dizer é que a gente constrói essa função tomando as condições que a gente tem de nosso processo e escreve o t em função, o x em função do t e do x0, e aí a gente faz toda a transformação. Então, quando você tem mais condições no sistema, no processo, essa função fica mais difícil de manipular. Tá. Mas interpretação nesse momento não tenho.
Talvez eu também não... Can you comment on the proof of the central limit theorems?
É muito boa essa pergunta, mas é realmente bem pesada a prova, e por isso eu quis poupar na apresentação. Mas se você quiser, se estiver interessada, eu te posso o arquivo, o paper está no archive e a gente pode se encontrar mesmo online, tem que ser online, e eu te posso dizer como foi, tá? E legal que você se interesse por essa prova, mas é longa e é pesada, mas é legal. Se você quiser, eu posso mandar.
Eu tinha outra pergunta. Talvez porque eu estava pensando na função f para ver se eu conseguia achar alguma insight dela, mas eu não sei se estava no teu resultado. Qual que é eu vi que quando o teu K aumenta, quanto mais spreaders tu precisa para passar um ignorante para um spreader, decai a proporção de ignorantes no final, né? Que é o de se esperar.
Isso.
Mas tem um K máximo que tu vai chegar a anular a coisa? Não vai ter nenhum ignorante no final? Vocês chegam a ter um K estrela, tal que para qualquer K para cima tu não tenha mais ignorantes?
Sim, quando o K... Bom, o processo parece que atinge esse cara. Ou seja, o processo parece que tem um K onde já a proporção de ignorantes é muito, muito, muito pequena. E em 10, neste gráfico, já aparece bem pequena.
Ah, tá, mas vocês não provaram a existência de um K crítico.
Mas a gente não provou a existência de um K crítico, e eu acredito, chuto, mesmo que deve existir.
Mas no teu teorema não tem o resultado do teu X infinito, não depende de K?
Não. A gente não mexeu com isso.
Ah, tá bom. Talvez só no limite, essa que é a minha pergunta, porque por isso que eu perguntei, que talvez seja só no limite, não necessariamente exista um K crítico, né?
Pode ser.
Nós temos mais alguma pergunta?
Boa tarde.
Pode falar.
Qual dos dois? Tá, vou fazer a minha pergunta, então.
Ok.
No seu modelo, vocês introduziram, então, esse tipo de um aware, dois aware, é tipo uma pessoa que sabe o rumor, mas ainda não dissemina ele. Eu queria saber só se vocês chegaram a pensar em... Que, para mim, não sei, eu acho um pouco estranho uma pessoa que começa a disseminar o rumor parar de disseminar assim que ela encontra outra pessoa que saiba o rumor. Então, talvez fosse interessante pensar em tipos diferentes de spreader, tipo, uma pessoa que ouviu o rumor várias vezes depois, não sei, só pensando, assim, se vocês chegaram a pensar em algo nesse sentido, ou se é equivalente...
Nesse sentido, não, mas o que você disse é bem legal. O que a gente vai focar, estamos pensando agora, é focar um pouquinho no que é esparcido, sabe? Não é tipo, mas está mais ou menos caminhando no que você está falando, eu acho. Não é pensar em tipos de informantes, sino mais focar no que ele está esparcindo, talvez. Focar na informação. Talvez isso faça com que a gente tenha mais tipo de informantes, pode ser. Mas apenas estamos amadurecendo a ideia, realmente.
Ah, legal.
Claro, Elcio. Bem-vindo. Entra.
Bom, boa tarde a todos. Estão me ouvindo?
Sim.
Sim.
Não, então, respondendo ao Daniel, isso já foi... Se eu entendi a sua pergunta, isso já foi estudado.
Ah, sim.
A tua pergunta foi no sentido de que a pessoa... Justamente, foi o contrário. Essa foi a proposta que motivou o nosso artigo. Quer dizer, pelo que eu entendi, a tua pergunta é no sentido de... bom, estou falando em português, mas acho que a linguagem já mudou, então eu sigo no português. A tua pergunta foi no sentido de que a pessoa espere um determinado número de vezes até se tornar fofoqueiro. Eu chamo spreader em português de fofoqueiro, é isso?
Sim.
Não, então isso já naqueles artigos de 2011 a gente já resolveu. Na verdade, essa ideia já está no original, no artigo de 67, do Decay. Essa ideia eles lá chamam de K-fold spreader, ou seja, o cara que vai esperar K vezes ouvir o rumor para se tornar fofoqueiro. E, na realidade, o que a gente fez agora foi uma motivação baseada no que um referi desse artigo original de 2011 falou para nós. E se for o contrário? A pessoa vai no sentido oposto e agora ela para virar... Antes era para se virar fofoqueiro, agora você... No sentido aware, no sentido de ouvir, mas não sair contando, né? Então, agora o que talvez valha a pena pensar, mas acho que vai ser difícil, é misturar os dois casos. Então, você tem um K e um K'. Tá pelo menos nos meus planos.
Legal.
Não sei se você entendeu, mas é um resumo aí.
Eu compreendi, sim. Já respondeu a pergunta. Obrigado.
Nada, imagina.
Mais alguém tinha uma pergunta, acho, né?
Boa tarde, pessoal. Então, eu vou fazer a pergunta em português também, né? Aproveitando
Tá bom, faz.
Então, eu vi que você apresentou, né, um limite central nos últimos dos slides, né? E aí você falou que a prova, né, é um pouco intensa, né, complicada, né? Tem um processo elaborado, né?
Isso.
E aí eu queria saber Bom, se é possível, vocês pensaram talvez em fazer uma extensão da convergência distribucional, né, para, por exemplo, se você troca de distância, né, por exemplo, em base tem distância, né, ou ainda mais geral, variação total, né. Em geral, nem sempre pode ser que não seja possível, né. Eu queria saber se, talvez, nos passos da prova, né, talvez dá para, da prova do TLC, talvez dá para fazer uma extensão. Não queria saber se você pensaram nesse sentido.
Não sei se dá, porque não tínhamos, bom, eu pelo menos não tinha pensado nisso. Então, não sei se dá, teria que olhar e ver se dá para estender como no sentido que você está propondo. Não, então, teria que olhar e, assim nesse momento, eu te falo que não sei.
Ah, legal. Então, obrigado pela resposta. Em geral, teria que ver os pontos principais da prova do TLC, né, e depois ver se é possível fazer uma extensão para outra distância, né. Então, tá bom. Obrigado.
De nada.
Mais alguém tem alguma pergunta? Se não, vamos ligar os microfones e agradecer a Alejandra. Obrigada, Alejandra.
A você, por me convidar.